In this video, we are going to discuss some counting problems based on everything that we covered so far. If you are new to the topic, then I suggest watching all the previous parts of this series first. The first question is from the homework exercise of the previous video. Skiers at the top of a mountain have a variety of choices as they head down. At each intersection, a skier is equally likely to go left or right. Find the percentage of skiers who end up at C or D. So we have people descending from the top of this mountain, going down along these trails to reach these bottom points. When at top, a skier has two choices to go down one step, left or right. After one step down, if he is at this point, he again has two ways to go down. Or if he is at this point, he still has two choices for going down. So either ways, he can go down in two different ways. Going further, at this level, he may end up at any one of these intersection points. But no matter what the intersection point he is at, he always has exactly two options to go further down. Similarly, at any level, skier has to continue choosing between left or right to go further down. So total number of ways in which a skier can get down is 32. Now let us look at those ways in which a skier can get down and end up at bottom point C. Observe that to reach C, skier has to take 2 rights and 3 lefts. The order of rights and lefts do not matter. As long as there are 2 rights and 3 lefts, he will always end up at C. And the total ways in which we can order 2 rights and 3 lefts is 5 factorial by 2 factorial times 3 factorial, that is 10. So we can reach C in a total of 10 ways. Now for point D, observe that D is 3 units on the right side from the leftmost point A and 2 units on the left side from the rightmost point F. So if a skier takes 3 right turns and 2 left turns in any order, he will always be reaching point D. And 3 right, 2 lefts can be ordered in 10 ways. So the number of ways in which skier can end up at point C or D is 20, and the likely chances of it in percentage is 62.5%. The next question is also from the exercise of previous video. We have 5 plus signs and 4 minus signs, and we have to arrange these symbols such that minus signs are all separated and no two of them are together. Recall that in such cases of strict separation, we need to arrange the separators first. So we arrange plus signs first. Arranging these 5 plus signs among themselves doesn't give us any new pattern. It's always 5 plus signs next to each other. So these can be arranged in just one way. We can think like 5 plus signs can be arranged in 5 factorial ways. And since all 5 signs are identical, so we divide by 5 factorial, getting the number of arrangements as 1. In between these plus signs, there are 6 places. Now if we arrange the minus signs on these places, there will be no chance of any 2 minus signs being next to each other. And 4 minus signs on 6 places can be arranged in 6p4 ways. But since all 4 minus signs are identical, we divide by 4 factorial. So 5 plus signs can be arranged in one way, and 4 minus signs can be arranged in 6p4 by 4 factorial ways. By counting principle, total arrangements is 15. The next question is also from the exercise of previous video. We have this set of 6 A's and 5 B's. We need to arrange them in such a way that the subscripts of A's are in ascending order as well as that of B's are in ascending order. So we can rearrange them however we like, but always maintaining that order in A's as well as in B's. To do so, consider 6 squares for 6 A's and 5 triangles for 5 B's and arrange them. Since squares represent A's and also because A's have to be in order, so the first square is A1, next square is A2, next is A3 and so on. Similarly, triangles represent B and B's are also in order, so first triangle is B1, second is B2 and so on. So any arrangement of these squares and triangles correspond to a unique required arrangement of A's and B's. So total number of required arrangements is equal to the total arrangements of 6 squares and 5 triangles, which can be done in 11 factorial by 6 factorial times 5 factorial ways, which is the required answer. We may turn this entire thought process into a simple rule that in an arrangement, those things that have to be in some order should be treated as identicals. As we are arranging a total of 11 objects, so 11 factorial, and since 6 A's have to be in given order, so we consider them identical and divide by 6 factorial. Also 5 B's have to be in order, so we consider even them as identical and divide by 5 factorial. The next question is also similar and is based on ordering. A spider has 8 legs and it has 1 sock and 1 shoe for each of its 8 legs, which means this leg has its own sock and shoe and they won't go with any other leg. Similarly, every other leg has its own pair. Let us number these legs so that we can assign them their pair of sock and shoes. Let S represent the socks and B represent shoes, where this pair, for example S6B6, belongs to the 6th leg, or this pair S3B3 won't go with any other leg except the 3rd leg. We need to find the number of ways in which this spider can put on these 8 pair of sock and shoes so that on any leg the sock goes before the shoe. An example arrangement can be this. Notice how any shoe is always placed after its corresponding sock. So we have 4th shoe ordered after 4th sock, 6th shoe after 6th sock, and so on. Since we are arranging a total of 16 things, 8 socks and 8 shoes, so total ways will be 16 factorial. But since S1 and B1 have to be in order, with B1 always placed after S1, so as discussed in earlier example, we consider them identical and divide by 2 factorial. Again, since S2, B2 have to be in order, with B2 always after S2, we consider them identical and divide by 2 factorial. Proceeding similarly for all these 8 pairs, we divide by 2 factorial for 8 times, and thus we have the required number of ways. The next question is, if 3 dice are thrown, then in how many ways can we get an outcome that is in ascending order? So if we throw 3 dice, we may get 4, 3 and 6, but we don't want that, as 4, 3, 6 is not in ascending order. We want to have outcomes like 1, 5, 6 or 1, 3, 4 or 3, 4, 6 and so on. And to find such outcomes where the numbers are in ascending order, we need to focus on the outcome of the middle die. Middle die's number is important because both the left and the right die's number depend on it. For any given middle die's number, the left die must show less, while the right die must show a greater number. Let us look at all the possibilities for the middle die. If the middle die shows 1, then the left die will have no choice as it can't be any smaller than 1. So we have 0 outcomes with middle die showing 1. If the middle die shows 2, then the left die can show a smaller number in just one way. It has to show 1. The right die can show a greater number, that is 3 or 4 or 5 or 6 in 4 ways. So by counting principle, we have 4 outcomes with middle die showing 2. If the middle die shows 3, then the left die can show either 1 or 2. So it has 2 choices. The right die can show a number greater than 3, that is 4 or 5 or 6 in 3 ways. So we have a total of 6 outcomes with middle die showing 3. Similarly, if middle die shows 4, then the left die can show 1 or 2 or 3 in 3 ways, while the right die can show either 5 or 6 in 2 ways. So we have a total of 6 outcomes with middle die showing 4. If the middle die shows 5, then the left die can show any number from 1 to 4 in 4 ways, while the right die can only show 6. so it has only one choice, which gives us 4 ascending order arrangements with middle die showing 5. If the middle die shows 6, then there is no way to form an ascending order arrangement because the third die cannot show a number higher than 6. Since the above possibilities for the middle die are all mutually exclusive, so the total number of required outcomes is this sum, 20. That is all for this video. In the next video, we will be discussing the cyclic order in arrangements and circular permutations. Meanwhile, you should go through questions from any book that you have, and in case of any doubt, you can let me know at this address.